morning, good afternoon, or good evening from wherever you're joining us, and welcome back to the Learn with LINX series. It's fantastic to see so many of you tuning in from around the world. I even recognise a few familiar names, so welcome back. It's great to have you with us again. My name is Holly, and I'm part of the marketing team here at LINX. If this is your first time joining us, Learn with LINX is our ongoing series of free virtual training sessions and webinars, bringing together a wide range of industry experts. Over the years, we've covered topics like Wireshark, DNS, BGP, IPv6, and even the fundamentals like what is an internet exchange and how to use the LINX portal. You can catch up on all our past sessions anytime over on our YouTube channel. All you have to do is search for @LINX Network. Today's session is also being recorded and will be available on our YouTube channel shortly after we wrap up. In just a moment, I'll hand you over to our training expert, Richard, but before that, a little bit of housekeeping. This is a webinar, so if you'd like to ask a question, just use the Q&A button on your Zoom toolbar. I'll be keeping an eye on these and pass your questions over to Richard throughout the session, so don't feel like you have to wait until the end. We've explored a wide range of topics and we hope to bring value to the community, but we'd love to hear your suggestions too. So feel free to drop us an email at marketing@linx.net or share your ideas in the chat. You never know, it might inspire others as well, and we love collaborating with you. But that's enough for me. Let's get started. Richard, over to you.
Okay, thanks, Holly. Right, so I better share my screen, eh? So there we go, everybody. Can you see that okay, Holly?
Yep, all good.
Yeah, excellent. Great stuff. So this is a webinar about peering, everybody. There are a couple of demonstrations throughout the proceedings showing peering in itself. But apart from that, it should be all pretty good. So we'll make a start and see what comes up. Okay, right. Yeah, so here are the sections. The first part is really just an introductory session, and like it says, it's covering terminology. It's a good idea for you to know, not least what peering is and all that, followed through by a peering section in itself. And there are a couple of demonstrations in there, just showing exactly what's going on, essentially. Then pretty much in the second, what we'll do, we'll have a break after about an hour. So one could argue that it's almost in two sections, sections 1 and 2, and maybe a part of section 3, break, and then back to finish things off. Okay, so that's the format, and we'll see what happens. The peering best practices. There is something that is reasonably important for you to keep your eyes open for, and it's actually covered in section 3, the route aggregation. I'll be giving a practical demonstration on how to aggregate routes using BGP, which of course has the knock-on effect into the routing table, etc. So, and then you will also find it's declared in the peering best practices aggregation. So there we go. That's what the flow of the course will be. So we'll make a start. So here's chapter 1, the introduction. And like I say, it's just covering a bit of terminology that you just need to be aware of at least. Okay. So we'll see what it has to say for itself. I'm just going to make sure I haven't just 2 slides. Yeah, here we go. So you can see there is a bit of a topology at the bottom there, making use of internet exchange points, multiple service providers all hooking into edge devices, and they are then all connected via some kind of switching mechanism internally. So anyhow, things you just need to be aware of within here is that a network operator is an entity running a TCP/IP-based network, yeah, the infrastructure. And this will provide access to end users and other network operators. Yeah, the end users in themselves, they can be anything you can think of, really. Residential businesses, etc., content developers, all hosts. Whereas other network operators, they are providers, basically. The internet is hierarchical. You will find there is a bit of a tiered structure, yeah, tier 1, tier 2, tier 3 service providers. And this is the kind of mechanism that works for us. Yeah. So the internet is hierarchical, as I say, and some network providers, they will provide internet access to other network operators. So that's what the idea is, this hierarchy. So as I say, a tier 1 will provide access to tier 2 operators. They in turn will provide access to a tier 3 operator. Consequently, everyone has access in some way, shape or form, and it's what makes the world go round. Okay, and like I just put in here, some network operators do provide internet access to other network operator, whereas others might also provide internet access to end users. Fine, sounds reasonable. I don't know if I'm supposed to name drop at all, but I actually use Virgin, and obviously I'm an end user, so they provide access for me. So fine. So there we go. Two more terms here, access and peering. Well, of course, this is not entirely new for anybody, I wouldn't imagine, but access, yeah, the primary goal of a network operator here is providing internet access to their users or their customers. Yeah, these customers could, of course, be end users in themselves, or they could be other network operators providing access for other people. Fine. Whereas peering, I don't know, it covers a multitude of sins, but essentially it is making a connection. Yeah, peering is the connection of one operator to another operator to exchange traffic originated by other network operators. You could argue, are they neighbours? Well, they're not necessarily directly connected neighbours, but they are peers because they will be peering via another operator who might be a directly connected neighbour. So, fine. You'll come up various other little phrases related to this peering. They'll be private or public, etc., as we'll see as we go through. Yeah, when you've got peering, you are connected between multiple operators. If there is no charge, this tends to be called settlement-free peering. Fine, there's no charge as such. That'll be contradicted to an extent a bit later on when we find about transit and non-transit, basically. The peering can be private or it can be public. Well, again, broadly speaking, yeah, public, you would be peering via an internet exchange point, whereas private, you might have a direct connection into wherever you're going. Okay, and that's just what I've got saying down here. I'm just going to move my screen so I can see what's going on. So private peering here is where there's a private connection between two network operators. Sounds reasonable. It's private peering, so you get a private connection there, and the purpose being to exchange traffic. Absolutely. And like I just said, public peering takes place at a public peering point, an IXP, an internet exchange point, of which LINX is one. Here, good term to be aware of, transit. Transit is the purchasing of internet access by a network operator from another network operator, known as their upstream. So these would be upstream. You would be downloading into your system. It will be an upstream connection, and you pay for that traffic. All right, fine. Transit is the first thing a newcomer network operator will require when they're trying to get their internet going. Sounds reasonable, because that's the name of the game. It does cost. Transit costs money, and it can be a pretty big expense for anybody requiring internet access from whoever they want access from. Yeah. So sorry to be so vague there, but that is transit. It is purchasing of internet access. Fine. Any network, interestingly, any network operator can participate in an IXP. Yeah. You do have to have certain requirements, not the least. It's a good idea to know what you're doing. Yeah. Fine. Consequently, you'll have your own public IP address space. Sounds reasonable? You wouldn't dream of using a private IP because you wouldn't be able to get on the internet anyway. Yeah. So you have your own public IP address space. You will have your own AS number. These AS numbers, they can be 16-bit, they can be 32-bit, these numbers, right? If I just stick with the 16-bit ones for the moment, 2 to the 16th is 65,536. So the range is from 0 to 65535. Fine. Within that, starting at 0, going to 64511 are the public AS numbers, and 64512 to 65535 are the private AS numbers. Fabulous. These private AS numbers, again, similar to the RFC 1918 IP addresses, private, they are not allowed on the internet. Yeah, so service providers have to take steps and means to make sure you can have access. All right, but in this case, you would have to have your own public AS number. Now this AS number is a big deal. Yeah, if anybody spotted the BGP one I did the other day, I made exactly the same statements there, that the AS number is a big deal. It is an identifier. Yeah, like I just said, it is a number and it is an identifier for an entity on the internet. Fine. Everybody on running the IXP type functions and accessing will have their own AS number. The AS number itself is also very useful for tracking where information has come from. You will see exactly what I mean in the first demonstration, where I'll tell you a little bit about it. Okay, so you need your own public IP address space, not 10 dot something, not 172.16.00 to 172.31.255.255, and not 192.168, and not any other reserved numbers. Okay, you will have your own transit arrangements. Yeah, because you are setting up your transit arrangements, you are paying for access from somewhere. Fantastic. It will be helpful if you can configure and use BGP. Yeah, you've got to be able to do this. You have to demonstrate familiarity with all of these topics to the suppliers. In this case, we'll say RIPE, Réseau IP Européens. They are the regional internet registrar for, in our case, Europe, but there are others throughout the world. So you cannot just jump on. Okay, so you need to be aware of that. Here's an IXP. The IXP, yeah, the central point. If I just jump back a slide, we can see here. Here's my IXP down here, multiple service providers all connecting with the edge devices. Fantastico. So an IXP is an open, it is a neutral interconnect. Yeah. So it means that, So it is an open, neutral interconnect where network operators can freely interconnect. When it says freely, you have to be a member. You can't just get onto it any old willy-nilly. You have to be a member. They can freely interconnect for the purpose of exchanging traffic. And within that, there are different ways, means, and declarations coming into it. Sorry, excuse me. So one of these is open. This means that the physical infrastructure provided for interconnecting networks is open to anybody. Any and all network operators can participate in that. Fine. Each network operator, we've already said, they have to meet certain requirements, public IP address space, AS number, etc. Each network operator is responsible for their own connectivity to the interconnect location, the IXP. That's what the open means. Just like open standard, really. Everybody could use it, but they've got to adhere to the terminologies. Neutral means that the physical infrastructure here, provided for interconnected networks, is not owned or operated by any one network operator. Yeah. Each member has an equal opportunity to participate, and nobody has an advantage. Absolutely. So that's open, neutral. Freely means the network operator participating in the IXP arrangement can choose who they want to peer with according to their business requirements. Fine. So that sounds pretty open and pretty free to me. IXPs themselves, typically hosted by data center or housing organizations, fine, and it's a 24/7 operation. Absolutely. There's our physical infrastructure. Yeah, it is a switch. Yeah, so it's no coincidence I've got a switch here. The interconnect medium of the IXP itself is an Ethernet switch. Yeah, these could be a good old size switch. Yeah, then in themselves, they will decide what you are having. Yeah, they support these dual personality ports, 1 gig, 10 gig, and that in itself is determined by the device itself, whatever it can be plugged into it. Fine. So if it's a switch, one would say here, it's a layer 2 arrangement. Transit like I've said, is purchasing of internet access by a network operator from an upstream provider. Fine. So the upstream provider will contact you. You will be in connection with it. Data will flow. Fine. The costs, transit costs. The vast majority of transit attracts traffic charges. Yep, they are levied. The charges themselves are levied on traffic levels, and they will be measured monthly basis. You will be committing to what you think you want. Yeah, it stands to reason that the charges, they will vary from region to region and how much you decide to commit to. If you want a low throughput, like I've got the example here, 100 megabits per second, that will have a higher charge than would gigabits per second. Yeah, okay. But I mean, so it's a sliding scale, as it were. Yeah. So within there, then you need to choose a transit provider. Within there, you've got the cost of the link. Fine. The cost of the links, plural. Yeah. Because if you're going to be using this on a big deal, you aren't going to be wanting to be reliant on a single connection. Yeah. So you want multiple connections. So fine. How reliable are these links going to be? Hopefully very, because again, you cannot afford to lose the connection at all. Yeah. So you need the reliability of the link and of the provider themselves. The service, what service is going to be offered? How good is the service? You need a good throughput. Latency, well, latency, jitter, it goes without saying that you really want as little latency as you can, and ideally, well, no jitter, but fine. Jitter, if anyone's a bit unsure about what it is, it's the variation in latency. Yeah. So you might have a delay, we'll say, of, I don't know, 100 milliseconds, then you have another delay of 50 milliseconds, then another delay of 800 milliseconds. That would be jitter. It is a variation in delay. So latency, jitter, etc. are important. Unsurprisingly, bandwidth is also going to come into this. The greater the bandwidth you want, the greater the bandwidth you can have, the greater the bandwidth you have to pay for. Fine. And finally, what else does the transit provider offer you? How diverse are their offerings? What can they give you? Do they do that sliding scale? Yes, they do. How much is monitored, etc. So you can see what's happening. Here again, peering. So peering is the connection of one network operator to another. Simple as that. Yeah. In order to exchange traffic. Absolutely right. Yeah. Two forms to it: private peering, mentioned it, public peering. All right. The network operators, you need a good understanding of BGP. Absolutely. Yeah. I mean, BGP is clouded in mystique and all this, quite rightly so, in how it works, but you need to be able to find your way around it. Fair enough. Private peering is where there is a private connection between two network operators to exchange traffic. It can be known as a PNI, a private network interconnect. Fine. The physical interconnect itself is owned jointly by the two operators and can differ. Yeah. So it could be fiber or it could be a copper cross connect. Yeah. To a long haul. Absolutely right. That's private peering. Public peering takes place at a public peering point, the IXP. Absolutely. And there you go. So now here, what one could argue here, we've got a direct connection coming into here. It might be private, yeah, might be a private connection into it, or it can just a straightforward public one. Operators peer with each other, so we are now peering all the way through. This device here is not directly connected to this system up here. Instead, it is paired like so. So this takes away that neighbours thing I was mentioned earlier. All right. They do this in order to reduce costs. It sounds reasonable. Yeah. If this device in the bottom corner, if it wanted to connect with the other 5 service providers, it would need 5 connections. Yeah. Without an IXP. For your information here, if we have these 6 devices and we want them to all speak with each other without an IXP, yeah, they would need a fully meshed network. which is fine. All right. Now, six devices here, there's a little formula. 6, where 6 is the number of nodes, right? 6 multiplied by the number of nodes minus 1. So that'll be 6 multiplied by 5 divided by 2. 6 times 5 is 30, divided by 2 is 15. You would need 15 connections for all of these devices to communicate. Whereas here, we don't have, because we're not using a full mesh, we are using a fully peered system. So it helps reduce costs, helps reduce complexity, helps reduce the number of connections. Fine. Because this thing is working here centrally, it will help reduce latency. Yeah, we've got the layer 2 type switching going on. It will help reduce latency. It will improve service quality. You can have access all over the place. You are peering with these upstream devices. Fine. In effect, the bandwidth is unlimited. Well, of course, it's not. It's monitored, but it's unlimited. Yeah, and you can also have a direct relationship, like I said earlier, with the other operators. Fine, all well and good. So hopefully that'll have thrown a bit of light into the terminology. Okay. Chapter 2. At the end of this chapter, you'll be able to describe what peering is, talk a little bit about public and private peering, and go on a bit further. Okay. So here is the internet, all looking quite happy with itself. It is a collection of separate and distinct networks. Absolutely. These things are the autonomous systems. Like I say, they can have a 16-bit number, they can have a 32-bit number, which can be a proper number, or it could be two 16-bit numbers adjacent to each other. Yeah, fine. So it, in effect, gives you 32 bits. Fine. They are still the identifier of the system. Absolutely. So here, I'm just going to read this first sentence again, because there's quite a big deal in here. So the internet is a collection of separate and distinct networks known as ASs, autonomous systems, with each system having their globally unique IP addresses, one of the fundamental requirements, and a BGP routing policy. You will remember, I said you have to have a globally unique IP address, yeah, the public one, and the policy. The policy is a big deal. An autonomous system is a collection of devices that run under a single administrative policy, ideally, yeah? And it's this routing policy here that is going to affect how your system works, okay? You might say, your policy might say, we want to aggregate all of our connections, yeah, if we can. Our traffic, we want to aggregate it as much as we can. Good for you. It's best practice, good for you. You might not. That is your policy, yeah? And again, thing to be aware of, if you make any changes to your system, particularly on the interconnections, that will be construed as being a change to your policy. You need to let the devices know in some way, shape, or form that you have made changes. Fine. You'll see what I mean when we come across it. Okay? This interconnection relationship between ASs is one of these types. It is peering, where the networks exchange traffic between their users for the mutual benefit, or it's a transit. So we've already said about transit. One network, a downstream system, will pay for an upstream access. So one network pays another for access to the internet. Fine. A definition of network peering, there's one or two of these, yeah, is a voluntary connection of administratively separate internet networks, ASs, the voluntary connection of admin separate autonomous systems, ASs, to enable the exchange of data between the downstream users of each network. So yeah, so here, this big ISP at the top here, that is a downstream system. They are making the connection to get the information to pass on to here. So one could argue that this could be a tier 1, this could be a tier 2 provider, and this could be a tier 3. You could argue all sorts. So there it is. So peering is a mutual agreement to exchange traffic between two networks without the networks paying for their service. That's peering. Peering enables businesses to reduce traffic costs while increasing performance and reliability. Absolutely, because we are connected all over the place. Absolutely right. Internet peering is free of charge, neither party paying the traffic exchange. Fine. Here again, network peering is that voluntary connection of administratively separate internet networks to exchange traffic between downstream users. Fine. Peering is free of charge. Yeah, transit is not. Just thought I'd mention it. So neither party pays the other regarding the exchange of traffic. Instead, the party will obtain revenue from its customers. Fine. Of course, you still have charges for the connections, etc., and everything like that. Absolutely. The peering agreement by two or more networks is set up like this. It can be a physical interconnection of the networks, absolutely, which is pretty much what we've got going on here, or it can be by an exchange of routing information via BGP, Border Gateway Protocol. You will see as we progress through the course, there are two, dare I say, flavors of BGP. There is IBGP, internal BGP, and there is eBGP, external BGP. This internal and external is quite important because it is stating the relationship to the autonomous system, to the AS. Yeah, internal BGP runs within an AS. External BGP runs between ASs. So it runs external to your devices. Yeah. Okay. So there you go. So there's IBGP and eBGP. We shall see them fleetingly as we move on. So here now, you've got these devices here, yeah, these systems, all ASs, all doing whatever they're doing. Fine. Here's a peering agreement here. The peering agreement between networks can be the physical interconnection. Absolutely right. And they've got them all over the place. Fine. Just making mention of the downstream user here, so one can see what I'm talking about. This would be the upstream neighbor, of course, and that would be the exchange of data coming across here. Similarly, this would be a downstream user of this device, and this is an upstream connection here. Marvelous. Facilitating this exchange of routed information is BGP. So now we can actually pick on this thing and say that, right, oh, good heavens, we've now got IBGP running up here, within here. This system here will have IBGP running in here, potentially. This one will have IBGP running here, potentially. They will then have eBGP connecting these two devices and eBGP here, because this is an exchange between this AS. We'll say this is AS number 10 and this is AS number 70. It really doesn't matter. But number 10 is not the same as number 70. So consequently, as this edge device here belongs to AS10, is talking to this device here, this edge device here, which is in AS70, they recognize that 10 is not 70 and 70 is not 10. So they are running between the different AS. Consequently, external BGP. Fine. Public peering involves creating connections between the networks using the public infrastructure. Yeah, so it's an IXP. While private peering uses private connections. Okay, and we still have BGP doing its bits and pieces down here. Absolutely. The peering agreements here allows these separate networks to exchange information. So you can see we've got multiple connections going on. Absolutely right. Dropped a few names in here, and still this info is being carried between these separate networks via BGP. So now, I said earlier, we could track where the information has come from. So if we said that Verizon communicates to BT, communicates into this internet up here, or better still, I suppose, AT&T communicate with Verizon, sorry. Hello. AT&T, sorry, I just, there, that's where I was. I'm just making sure I'm on the right slide. Yeah, so AT&T could communicate to Verizon, and Verizon could communicate to BT. So what I was hinting at is that in the traffic, you can see that, yes, data originated here, potentially, transited, if not the right word, crossed through Verizon and arrived at BT. That can all be followed. Fine. Would it be? There we go. BGP needs a way to differentiate between these separate networks, yeah, to recognize the different enterprises. It won't recognize its BT, it won't recognize its Verizon, it won't recognize its AT&T. So, important point here, an enterprise registering a desire to use the internet is issued an identifying number. You'll not be surprised to hear that this is the AS number, yeah. The identifying number is controlled by the internet authorities, the IANAs, and then down into the regional internet registrars. It's called the AS number, where AS is an autonomous system. It is a standalone system. Fine. That AS number can be 16 bits, as I've said, giving you a range of 065535, 65536 in total. Yeah, there. Some of these are reserved, not the least the private ones. All right, which will become relevant shortly. And you can see here, AT&T, I've made these numbers up. AT&T have an AS of 30500, Verizon have 1510, BT have that, and so on and so forth. So this here, BT, Verizon, and AT&T, they are all public AS numbers because they're between 0 and 64501. Whereas these here, we've got 64515 and 64523. Anything greater than 64501 is a private AS number. So I just dropped them in there just for the sake of illustration, really. The peering relationships are recognized by BGP, absolutely, because BGP is the carrier. So what I've got here is a quick demonstration for us just to have a look at these AS numbers in situ. All right, so I'm just going to bomb out of that and drop into a lab. Drop into a lab here. So you can see here, I've got 1, 2, 3, 4, 5 routers doing whatever these routers are doing, and they all have AS numbers. All right. 24123 is a public AS, 30500 is a public AS, 64523 is a private one, 1510. I've made these up. Yeah, they are of no relevance whatsoever, except for the fact that they are the identifying number. That is a big deal. You can also see I've got networks here, 10.10.10.10.0. I've got 10.10.11 somewhere, 10.10.11, 10.10.12, 10.10.13, and 10.10.14. So what we should be able to see here, if I drop it, he says going into the wrong place. If I call up a router here, and I'll just go into here, just do my little bits and pieces. There is a command which you may or may not be familiar with, which is quite a big deal. Just make this bigger. If I type in show IPBGP here, this, fantastic. That wasn't supposed to happen and shouldn't have happened. So I'll just have a look, see if another one's going to do exactly the same. BGP not active. This should not happen to a man of my age here. What I'm just going to do, chaps, bear with me. I'm just going to wipe the device. I'm just going to wipe the device. I'm just going to wipe the device. Oh, ho, ho. I'm just going to wipe the device. And then wipe the device. So that should have cleared all of these devices down, and I will restart them. This was all checked before we started. All right. So while I'm just waiting for those, because no doubt they'll take a few minutes to load, fantastic. What you will find in here, in these devices, there is a router, and it is displaying this network, 10.10.10.0. This one is displaying or using 10.10.13. Fine. What's going to happen I hope, is that all of these routes are going to be exchanged between the devices. Yeah. You will then see that the AS number in itself is used as an identifier within that BGP table that I mentioned. Okay, so that was just a valiant attempt there to try and use a bit of information. All right. So this lab is to introduce you to BGP. Fine. Each network installation is identified by a color. Fair enough. But more importantly, yeah, definitely more importantly, by an AS number. Big deal. Given that each of these installations can talk to each other, it is fair to say that AS64515, here it is, AS64515, can communicate with all the other ASs. Absolutely. It's also possible that multiple routes are available to some of these sites. Absolutely. So this is what we're going to try, hopefully, and see. So really what I'm saying here, AS64515, this one, if it wants to get to here, it could actually go this way, absolutely, to here, no problem at all. That would be one path. It could come this way, straight to here, straight to here. Absolutely. And there could be multiple other paths as well. So yeah, it could come back. I haven't put all the routes in, but of course it could go over the internet as well. All right. So all of this information will be collected because all of these connections are working on BGP. Okay. So I'll just see how this thing is going. So it's very... Holly, do you want to take a break for 5 minutes while these things load, or are you content to wait?
No, it's completely up to you.
Yeah? Yeah, if we take a break for 5 minutes then, because otherwise, because I'm just going to wait for these machines. I don't know why they've failed on me, but there you go.
No,
So
that's all right.
if
10
we could
minutes
do
enough?
that. Yeah.
So we'll all go back, get back, go have our coffees and our loo breaks, and then we'll be back at 10 to 11. So that's
Yeah,
10 minutes time.
that'll be fine, Holly. Thank you very
Thanks,
much.
everyone. Remember, get your questions in if you have any. Use the Q&A function and we can ask them to Richard when we get back.
So here we have these 5 routers. Again, the mysteriously disappearing routers. Each one of these has its own AS number, as you can see, and the ones I'm particularly looking at, I suppose, will be AS24123, which is using network 10.10.10.0, and AS64515, which is using internally network 10.10.13. Fine. But the point to all this is, if we just jump back to what was mentioned earlier, a potential suitor for using these systems needs to have a public IP address. They need to have an AS number, certainly. They need to know something about BGP. So if we now have a look at one of these articles here, I'll pick on AS64515. So if I just click on there, and we should get that, okay? This is where we got to last time. I will type in show IP BGP. I want to look at the BGP table. You will see why. So I'll just make this a bit bigger. Show IP BGP, press enter. This is what we should have got last time. You can see here that this is why you need to know BGP. There's a lot of information here, which is, quite interesting, really. So I'm just going to move across there so you can see what I'm talking about. I am looking at AS64515, this green one here. And it says its internal number, its internal network is 10.10.13. It is. And if we just have a quick look across here, we can see there's 10.10.10, this one here. There's 10.10.11, which is the one in the middle, 1510. There will be 10.10.12 over 10.10.12, that's this one. And there is 10.10.14 here, which is this one over here. And what we can see also that, yeah, it does make mention of 10.10.13, which you remember is its local network number. And it's this one here. What I particularly want you to be aware of is that in BGP, there are certain parameters that absolutely have to be exchanged between suitors, between peers. Yeah, and one of these that has to be included is the next hop IP. All right. Well, you can see here, this one has got a next hop IP of 0.0.0.0. So what that's saying is it doesn't mean it doesn't know where it is. It means that it is a local address. So this 10.10.13 is going somewhere internally and it is local. And if we just go a little bit further, we are now, BGP uses things called attributes, or it can use things called attributes. These can be used to affect how BGP works, how it operates. And as soon as we get to here, this metric, also known as an MED, also known as a multi-exit discriminator, is an attribute. The local preference is another attribute. And then there's this thing called the weight, which is another attribute. You can see there the weight is set to 32768. That 32768 is indicative of a local network. So now what you should be able to say is that, right, knowing my vast knowledge of BGP, I can see I have a local network of 10.10.13, which doesn't have a next hop because it's not going anywhere. I know these are metrics. I might not know much about them, but I know the metrics. And the weight is 32768. So that is confirming that it is locally generated. Fine. And those three things here are metrics. There is then another one here, right at the end. This is a big deal. This is the AS path metric. And you can see here, if we was now to have a look at this one here, just no particular reason other than it's the longest one. But what this line is telling you is that device AS 64515 can get to network 10.10.12. So if we just have a quick glance to see 10.10.12, see where it is, 10.10.10, 10.10.11, 10.10.12 is this one over here. All right. And it will then say, right, I have received this information from 10.10.12. Its next hop is 192.168.1.5. Well, if it is, it is. I'm quite prepared to take its word for it. But we can then carry on. There is still the metric, there's still the local preference, there is still this. But now you can see that the AS path attribute is actually populated. And what this is telling you is where the traffic has come from, what it has passed through, and how it's arrived, right? So if we look at it, we can see here, this, like I said, this is really quite important actually. The network 10.10.10.12 has originated, well, was originated in 30500. There it is. And there it is, look. There is 30500. That is the first number in that AS path. That is the origin. You need to remember that. You need to know that, right? So that is the origin. Then the information went to 64523. Well, it did, because it's here, look. It could have gone that way, but that's not relevant, So it went there. Then from here, it probably went to 1510. Let's have a look. It did. So it left 30500. Come on. Went through 64523, went through 1510. Then it went to 24123. Where's 24123? 24123 here. So actually, data from here, traffic went from here to here to here to here. Fantastic. And it worked. I mean, it's quite right. So what the big deal is to this, of course, is that now you can see, like I've said, where the data originated, where it crossed, and then it went through this one. And 24123 is the one that is closest to AS 64515. Fantastic. You can also see that not only could it go this way, there are multiple ways for this. This is why you need to read BGP, right? You can now see there is another path available to 10.10.10.12 with the next hop of 192.168.1.10. Well, again, I'm quite prepared to take its word for it, And we can see here, in this case, the traffic still originated in 30500. Well, of course it did. It wouldn't have any choice in that one. Yeah. Then it went to 64523. Then it went to 1510. So in other words, this other one, if I just move that out of the way, 3500, 1510. So it went this time, this path went here to here to here. Whereas previously, you'll remember, it went from here to here to here to here. Fine. So BGP can have a look at all that information and it will decide what it thinks is the best path. Right? So if I just make that smaller. So we can see here, yes, there are two paths available, and BGP has actually highlighted what it thinks is the best route. It's got this greater than sign. Yeah. So that greater than sign is indicating the best route. And the reason it's actually chosen that will be because it's got a shorter path. Yeah. In this case, it's got a shorter, fewer entries in the AS path attribute. That's how it works. So what that means is that given that it has these attributes, you might be perfectly happy that for traffic to come and go using that path. Good for you. Good for you. That's fine. But you can the BGP attributes can be manipulated, and you could actually make this the preferred route. Yeah, for whatever reason. Yeah, that would be dictated by your policy. So there we go. So this is all good stuff. Okay. It still follows, of course, that you've also got two paths to get to 10.10.10. Fine. And you've still got one of those. The bottom one is the best path, or what BGP thinks is the best path. And sure enough, there are fewer entries in the second entry, in the lower entry. Yeah, that will be relevant all the way through. 10.10.11 still has two paths. Again, the shorter one, fewer entries, that will be the chosen path. So there you go. Then, if hopefully you found that dead interesting, if I then type in this, show IP route, I can see what I've got here. Now look here. In fact, what I'll leave it as this. We can see on here somewhere, I will have network 10.10.13. There it is. 10.10.13 is directly connected. We know that. It's actually plugged into the thing. But what I'm really interested in is this. Show IP route BGP. I now, just bear with me, show IP BGP here. Those are routes that I can see using BGP. And I can also use this command, show IP route, BGP. And again, it will say, right, look, I have routes available to get to 10.10.10, 10.10.11, 10.10.12, 10.10.14. And I can get to these using BGP. How do I know? Because it says here, B for BGP. And it also, as we come along here, it will then show me this here, this 20/0. This is what they call the attribute. Yeah, it's not called the attribute at all. It's the admin distance. Yeah, and this is the external BGP has an admin distance of 20. So here, what the system is telling me is that I can get to all of these networks, and I will be using external BGP to get to all of them, which is absolutely bang on correct, because 10.10.10 is here. It is not in here. 10.10.11 is here. It is not in here. And similarly, these 10.14, etc., they are over here. They are not in there. So they are using external BGP. There is no internal BGP yet. Okay? So that is that for that lab. Yeah. So it showed us the AS path attribute, and you can see how useful it is, because if I just go back, you can use it to see where the data originated from. Absolutely. Yeah. Then where it passed through. This really is quite a big deal. Yeah. AS is it transited through, I'd say transited, crossed, and then finally this would be the AS that was next neighbouring. Yeah. So in this case, it is 24123 coming that path, which it certainly is. There's 24123 on its way in, and the other one was 1510. Again, that's fantastic. So There you go. Right, so that concludes that bit of a demonstration on there. So what I'll do now, I'll stop all these nodes, and then I shall close the lab, and then I shall load this one, and I shall get it all up and running, hopefully. Start all nodes. I'll just make sure these all turn blue. Yeah, so that looks pretty promising. Right, so we're back to our notes. Or back to my notes. So there it is. So that lab showed the BGP, the use of its AS numbers, and how data can transit between separate networks. Absolutely. Inside an AS 6423 here, it is fair to say this is just the same topology with a bit of an extension here. Fair to say that within many separate autonomous systems, there can be multiple different systems. By that I mean that here we've got AS 64523, just the same as I have in the lab, except here I am now pretending that this is in Europe. Consequently, I could then have multiple devices internally. And you can see here, I've got some in France, some in Sweden, some in UK. Why not? Why not? Yeah. And they are all members. This is supposed to be, or pretending to be, a multinational company that is based in Europe. Yeah. So they've got these offices in all of these places, but they are all members of the same AS. So now, what would be happening here? The UK sites would be able to communicate with Sweden and France, but then because they are internal to the AS64523, these would be using internal BGP, and we'll see that a bit later on. Yeah, the admin distance for internal BGP on these devices is 200. Yeah, so it's quite easy to distinguish between the two. But so, like I put here, it's fair to say that within many separate ASs, there can be multiple different systems, and there they are. Yeah, these could be geographically separate. UK, Sweden, and France are pretty geographically separate, but they don't have to be. Okay, so there you go. We will see that a bit later on. Okay, just making sure I've got the right things. Inside this AS64523 here, there are three separate networks. There's the UK, there's Sweden, there's France. Fine. They can use BGP to communicate with each other, certainly can, via the local area networks, and they will use a few other protocols to keep the system in sync. Yeah, fine. In order to exchange, to find each other and exchange information. These are the protocols. I've just put these in because I thought I should. Yeah, there is IP, the Internet Protocol, Layer 3 protocol. Then there are the two there are the two Layer 4 protocols, TCP and UDP. Fine. Routing protocols can also be used to move data between these networks. So what I'm saying here is that in the UK site of AS64523, they would have an IGP, an internal gateway protocol, working to build the links between the devices. In this case, it would probably be OSPF or ISIS. Similarly, Sweden would have a similar thing, and so would France. Then it would be nice to think that they would all use the same IGP, the internal gateway protocol. Yeah, because the policy would dictate it. Yeah, this policy for 64523 would dictate that we will run ISIS, we will run OSPF within our sites, and we will then use internal BGP to communicate between them. So, fine. Okay. And again, they all have these separate networks. Of course, they all have to have a separate network. I know I've used private IP addresses. It doesn't matter. You know, for the sake of example, it is perfectly happy. Okay. The LANs will each process all of their information and then send information up to this edge device here, which is then the path into the internet and into all the BGP exchanges that takes place. It's called an edge route, this one, because it is, of course, on the edge of that device, of that particular network. So fine. So this is where your external BGP would come into play, going upstream, and internal BGP would be for downstream devices, basically. So there we go. That's that. I'm not going to use that one. I'm using a different one. Okay. So how are the ASs connected then? Well, there's two types. We've already mentioned it. There is public peering. There is private peering. Yeah, the public peering. Layer 2 access technology is the fabric. Yeah, got multiple connections going all over the place. It looks like a piece of fabric. You got connections all over the place. Absolutely right. Multiple carriers interconnect with many other carriers, actually, across a single physical port. Fine. And these are network access points, or were known as network access points. They are now called IXPs, yeah, Internet Exchange Points. Fine. That is public peering. LINX is an IXP. It does public sharing. Okay. There is also private peering, absolutely, where it's a direct interconnection using a point-to-point link between just two networks. Sounds reasonable. It's private. You're not likely to have 7 or 8 of them in there. You know, complete contradiction of terms, but it does it. Yeah, across a layer 1 or a layer 2 medium. Fine. It is dedicated. It is private. It is yours. Yeah, fine. It's not shared by anybody else. It will be a good, reliable connection. Absolutely right. Fine. So there you have it. Public via the IXP, private not via the IXP. All right. And there we have it. That's the internet now, as it were. You've still got your ISP all over the place. You've got BGP running left, right, and centre, delivering traffic between the ASs. Life is good. And there's a tiny bit on the tiering I was talking about. Yeah, there are the tier 1s, there are the tier 2s, there are the tier 3s, and so on and so forth. Yeah, there's not tier 4 or 5s, right? Tier 1 are the big hitters of it all. Yeah, they will be dealing with the national service providers, BT in Britain's case. Yeah, so the tier 1s would come up to the tier 2s, and then the tier 2s would similarly communicate to the tier 3 providers. Okay, so there we have it. Peering and transit, just to reiterate, we now have our transit providers here all over the place, and you can see peering, it does nothing a great deal in here. We've just got the peering connections, whereas down here, we've got the transit connections with all of their money. So it's just to reiterate the fact that a transit is a cost. It is a paid for link. So if you provide transit to people, you have to make pretty sure that your service levels can stand it. Yeah. And there we have it. So now a peering arrangement, and you can see quite clearly here, we've got the IX here, the IXP here, a network down here, a provider up here, fine. Public peering commonly performed at an IX, and it's a physical location here. Absolutely, it's that neutral meeting point. We know that. Yeah, you've got the same thing here, but we also have a private connection as well. Yep. So that just illustrates private and public peering. Okay. Oops. Yep. Here is the IX. Yeah, the IX, the IXP. So now we've still got our edge devices, of course we have. Yeah. And then we've got our customer edge devices. Then we've got our edge devices here. Peering takes place, absolutely. And you can see ingresses, data will ingress and egress here, yeah, through this layer 2 infrastructure, and out it comes. So peering, that is the IX architecture. Layer 2 core, if you like, and the layer 3 edge devices, potentially. Root servers are in there. Good heavens, what can these root servers do? Well, these here, this is not me, by the way, it's just the computer that's decided to have a bit of a minute for itself. Yeah, in a root server's case, here, instead of these root servers peering with everyone, yeah, the service provider only needs to peer with the root server. So yeah, there we go. So this is now peered here. All of these are peered to the root server, and the root server is taking the job of other devices and allocating traffic. Okay, so that's the point of the root server. And there we have it. So now this one here, this root aggregation is more than one might think, because it is aggregation, it is summarization, call it what you like. And the idea here is to save routing table space, save memory. Yeah, so that's what we'll be looking at. I'll be using this to illustrate IBGP and eBGP and the aggregation itself. All right, so so at the end of it, you should be aware about aggregation and the benefits. Fine. The benefits are it's a smaller routing table. Yeah, simple as that. Why do I make a big deal of it? Because you can see here, there are quite a few entries, active BGP entries, the forwarded information database here. There's quite a few of them. It can be seen from the graph that there are many entries in the forwarded information database. It is possible to reduce this by summarizing or aggregating the advertised networks. It is considered to be good practice. Not only that, there are some sites that you can have a look on where they will highlight sites that could benefit from aggregating. Yeah. So if you can aggregate data, you really should consider it. The only tricky thing to this is your networks need to be contiguous, right? You couldn't aggregate something, we'll say, I'll stick with me tens. I know I shouldn't. You couldn't aggregate 10.10.10.0 with 10.10.47.0 and 10.10.98.0, then 10.10.201.0. They need to be contiguous. Yeah, not continuous, although it does look pretty similar. You will see what I mean. Okay, it's considered to be good practice. Fine. So we've got, let me just see what I've got here. Yeah. This would be a situation now where on this device here, I have some networks, 192.168.4, 192.168.5, 192.168.6. Fine, good for me. These are contiguous. By that, they mean they have the same similar bit patterns. Yeah, because the bit patterns here in 192 are set to be 128 would be on and 164 would be on. Well, the same applies here. The same applies here. It also applies down here. So you are looking for contiguous networks. Then what we will find is that these, because they are directly connected on here, they will be illustrated a line per network. Nothing you can do about that. That's just the way it is. Yeah. They would then, this information would then be passed up here, and we can see here that in this device's routing table, we've got 192.168, an entry for 192.168.4, we've got an entry for 192.168.5, and we've got an entry for 192.168.6. I mean, that's fine. Nothing wrong with that at all. Then, similarly, down here, we've got 192.168.8, 9, 10, 11, 12. And you can see again that, sure enough, on router 3, we have an entry for 8, 9, 10, 11, 12. Wonderful. Absolutely wonderful. Except the fact of the matter is that we have 1, 2, 3, 4, 5, 6, 7, 8 lines, 8 individual lines. If we wanted, we could reduce that. We could aggregate. You can believe you could have lots of these lines, and if you can aggregate it, it's better. So let's see what we can do. We can use this type of syntax. All right. So what I shall do, I'll just see if it's on the next slide, and I shall illustrate this thing now. So I'm going to go into here. Going to go into here. Fine. This is reasonably what we've got. All right. So you can see on this device here, moment of truth, everybody. If I click on here, it should work. I'll just type a couple of commands in. Well, that looks reasonably promising. So, and that's not what I wanted to do. Yeah, good. Right. I was just checking there. I lost a bit of confidence in my lab there. So what I'm saying here is that on this top device, I have networks 192.168.4.0, 5.0, and 6.0. And on the bottom one, I have 8.0, 9.0, 10.0, 11.0, 12.0, 13.0. These are all contiguous. So if I have a look on here, and I'll just bring this out of the way, if I type in on here, show IP route, we should find that we will have references to 192.168.4. There's 192.168.4, absolutely. There will be 192.168.5, absolutely. And there will be 192.168.6, absolutely. These are all directly connected. Yes, they are. They are plugged into the back of VIOS 1. Then if we have a look down a bit further, we can see, aha, there are also networks 192.168.8.0, 9.0, 10.0, 11.0, 12, 13.0. These are, of course, on this device here. Now, as I've just been at pains to point out, this device is a member of AS64512, VIOS 1, member of 64512. VIOS 2 is a member of 64512, and sure enough, VIOS 3 is also a member of 64512. Well, of course, if this is a member of 64512, that's a member of 64512, that's a member of 64512, that means they are all, talk about the obvious, yeah, they are all members of 64512. Consequently, they will communicate using internal BGP. And you can see here, sure enough, there's BGP down here, B for BGP, and there's all these networks on VIOS 2, and sure enough, the admin distance here is 200. That is internal BGP. That is absolutely fantastic. Yeah, fine. So everything is there. If I have a look on this one, we should see something reasonably similar. Show IP route BGP. Yeah. And you can see there. Yeah, the bottom device here, 64512B here, this bottom device is using internal BGP again to communicate with 192.168.4, 5, and 6. Good for it. Life is looking pretty good. All right, fine. So with that in mind, if I now go on to this one here, and I have a look in here, show IP BGP, that will show me the routes that I can communicate. Yeah, and you can see here, right, you can see here, this device has a separate line for 192.168.4, 192.168.5, 6, 8, 9, 10, 11, 12, 13. Well, that's fair enough. There's not too much we can do about that, really. But if we leave that one out of the way and just have a look at this one here, and we'll see what this one says, if anything. Go IP BGP. And again, this one also has access to networks 192.168.4, 8, 9, 10, 11, 12, 13. We have routes there. But there are individual entries in the routing table. It's taking up more space than it could do. All right. So what we'll do, we'll try and aggregate this thing here. If I go on to number 3, device number 3 here, and I do enable, fine, and I type in this, I'm going to configure something, and I'm going to go for route of BGP 64512. The BGP process, this is the BGP process identifier. It should match your AS number, all right? So now, with a bit of luck, I can now type in aggregate the address. You tend to pick, you don't tend, you do pick the lowest one of the bunch. So it's 192.168.4.0, fine. And then, can you believe I've, oh yeah, 255, 255, 252.0 and summary. Right, that should aggregate the addresses. Yeah, that's it. This here the 192.168.4 is, of course, the lowest network number out of all these, 4 or 5 or 6. This is the aggregation mask, yeah? And it's, I'll not go into that because it could get a bit lengthy, but that is the aggregation mask, and it's then going to send the summary only. So as we speak on VIOS 3, if we now have a look here, do show IP BGP, we'll see what we've got here. Look. What you can see now is that we've got an entry for number 4, fair enough. We've got an entry for number 5, and we've also got an entry for number 6. All right. But there is this thing which has been created. So this is part and parcel of the aggregation process. All right. So if I now come out of there, and I'll see what's happened up here, if anything. Show IP BGP. Look. This is fabulous because it's worked. Yeah, we can see that there is no longer an individual line for 4.0, 5.0, 6.0. They have been summarized. Yeah, they are in there. So now, instead of having 8 lines, we only have 1, 2, 3, 4, 5, probably about the same actually. 1, 2, 3, 4, 5, 6, 7. These others here haven't been summarized. Why not? I haven't told it to. But what should happen now, I could go back into here, and I can now type, if I go back to this previous command, what I typed, I could now type in 8.0. This time I know the aggregation mask is not that, it is this, 248. Oh, it's come out of here, sorry. Router BGP 64512, fine, aggregate address. Okay, it's 192.168. Again, you pick the lowest number. So, of course, in that bottom device here, the lowest network is 8.0. So I do that. Put my summarization mask, 248.0. Fine. Until I just want to send out the summary. And that, again, should have worked. So if I just save that, just for the fun and games of it. Don't know why I did that. Didn't really have to, but... Good. So that is now finished. So again, if I type in now show IP route, there we go. And we can see here, we've still got all of my individual routes here. Yeah, we've still got the internal routes. Yeah, IBGP, marvelous. Let's just see what we've got coming up onto here. Show BGP. How about that? How about that? So now, unfortunately, every time I close a session, it clears the previous one out. But you can see there that 192.168.4.0 has been summarized. So hiding behind this mask, there is 192.168.4, 192.168.5, 192.168.6. Hiding behind this mask here is 192.168.8, 9, 10, 11, 12, 13. So this, just, it might be a trivial example. It's not. It is. But instead of having 8 or 9 lines, you've just got 2. I mean, it's better. It's better. Yeah. So just to, at the risk of being terribly tedious, I could go back to here and config T, router BGP 64512. Fine. And I say no aggregate. 192.168, whoops. 168.8.0. 48.0. Fine. So now with a bit of luck, that'll have got rid of the aggregation process. And what I was hoping is that we would be able to see it. There you go. They're all back again. Yeah. So there you go. So that illustrates aggregation, etc. Yeah. And if I now type on here, show IP route BGP. And we can see on this device that most certainly is Vios 4 here, it is most certainly using external BGP to communicate. Absolutely. So there, within there, that's purely external. On here, see what we get on here. That one is just talking inwards, and that's using internal BGP to communicate with these devices. Okay. So that is the end of that demonstration there. So there it is. And there's my syntax. It's exactly what I've done. All right, it's BGP1. So what? No auto summary is turned off the class summarization. Here's the syntax that you're interested in. Aggregated S 201.4.0. Well, 201.4, 1.5, 1.6, 1.7. That's the lowest address for sure. And it just so happens that the 255, 255, 252 is applicable here. It is. So that syntax would now just comprise a single entry, 201.4/22, and it would cover 201.4, 201.5, 201.6, 201.7. Fabulous. The AS set here is that it will retain the information for the AS path. You know, if you don't do that, you do run the risk of losing the information, but that's not quite the end of the world. So what? Well, the so what is that there are various tools available for you to look at on the internet. Yeah, fine. All right, we'll see what they have to say. There is this one. This is quite pertinent. There is a CIDR report, CIDR, the classless interdomain routing report. Yeah, it gives daily updates. Gives daily updates regarding the internet routing tables, including a summary of the last week's changes in terms of routes that were withdrawn and added to the BGP process. Fine. How about this then? The aggregation report lists the top 30 ASs who, if they aggregated their announced prefixes, could make a good contribution to the reduction of the size of the table. Yeah. So you actually run the risk of being painted, bad. No, not bad. Irresponsible, maybe, or maybe not quite as responsible as you could be. Yeah, fine. But this is the point. It is public information. You can have a look at it. Yeah, you can get a list of ASs advertising routes that are more specific than the original registry allocation size. Fine. There is a possibility of bogons. Yeah, bogons, bogus IP addresses. They've not been released. Or they may have been released. Yeah. They won't. So what here? Whoops, sorry. So if we now just click into this just to see what there is within the CIDR report, fine. And then we just have to wait. And you can see here, these are readily available. Fine. There is summary of the total routing table for the past 7 days, a listing of possibly bogus routes and summary information on ASs. Fine. So all you have to do is just click on it. And it tells me, yeah, the 18th to 25th, the size of the prefixes. That's a good old size, 1 million or not. Fine. Yeah. How many were aggregated? Fine. The AS summary. There is also an aggregation summary here. Yeah. So everyone can see what's going on. Fine. The algorithm used in this report proposes aggregation only when there is a precise match using the AS path so as to preserve information. Aggregation is also proposed across various address spaces. But there you have it. So these are all available. The active BGP entries, you can check it out using that URL. It works. There's the aggregation report. Yeah. The networks aggregated, the net gain, what we would gain from all of this information. Yeah, great stuff. There is route views. There are quite a few of these tools. Yeah, fine. Route views, has routing collectors. You come across routing servers. Yeah, routing servers, they give information out. Route collectors take it all in. Fine. They are located all over the place. So you're going to get a good look. Amsterdam, London, etc. Yeah. More than 900 active peering sessions. Good heavens, it's certainly pretty global. It looks it. Over 260 organizations share routed information, including the big ISPs. Fine. They are based on this routing. It's FRR. It's a free open source routing protocol. Good for it. There are all of these other protocols. Good grief. BGP, OSPF, RIP. Wow. LDP, Label Distribution Protocol. Bidirectional forwarding. Loads of them. It has its roots in Quagga. Yeah. Quagga was an old flavor of Unix and the like. Here, root views, so you can see what's going on here. www.routviews.org. You can look into certain particular aspects of it. Yeah. IPv4, show me my BGP summary. IPv4, that show BGP summary is just as applicable in my labs. Could use that all the time. We can see who is doing what. Yeah, they're moving an awful lot of data. You've got the AS number. They're all running version 4. They have no choice. It has to be BGP version 4. Fine. And there's a section of that table. Yeah, the BGP routing table examined, whatever it was, fine. Prefix after maximum aggregation. Look at what? What? If that's it, BGP routing table entries examined here. How many after maximum aggregation? It's a lot less than that. Good heavens. Oh, there we have it. Maximum AS path, 84. Good heavens, that's some entries. So there you go. And the IPv6 as well, of course. Yeah, of course. IPv6 prefixes, etc. Marvelous. The looking glasses. LINX has the looking glass. Yeah. Looking glass servers are computers on the internet running one of a variety of publicly available software. Yeah, fine. It is accessed remotely to see what's going on. You can check to see if there's a problem somewhere. Have a look at the looking glass. It is limited. Limited. You can't change things, of course. Read-only portal to routers of whatever is running that looking glass server, and it's publicly available. Absolutely. IANA. We know IANA is responsible for allocating the addresses. Ultimately, come through the RIRs. Fine. 16-bit, 32-bit AS numbers. There you go. How about this? So now we could have a look. BGP, the Looking Glass website, for BT, for level 3, for goodness knows whoever. Yeah. There's the AS number, all in there. IPv4, is it all supported? Yes. IPv6, usually. So there's a lot to keep you entertained. RIPE, Réseau IP Européens. It is the one that looks after this part of the world. Yeah. RIPE is a large-scale, RIPE Stat is a large-scale information service on the RIPE Network Control Centers platform. Yeah, gives you a lot of essential information. Essential information on the IP address space being used and the AS numbers, various stats. Fine. So we can see what's going on in here. There. We can just go into there, into that, stat RIPE, see what happens. It comes up. It's already picked up something. AS509. It's just found out about mine. Fine. It's a member of NTL. Yeah. It's RIPE, look after it. They know it was allocated in here. Yeah, 1st of September. Fine. You can peer through all the way through it. Originated prefixes. All of this information can keep you going for hours. Yeah. So they are available for public scrutiny. Good. Peering DB, similar thing. Peering database is a freely available user-maintained database of networks. It facilitates a global interconnection of networks at IXPs. The database itself, non-profit, community-driven. Excellent. Promoted by volunteers. Wow. But again, it's here. Yeah, you can go into the peering DB database. You look by network, look by the organizations themselves, countries, whatever region. There is a lot of information. Absolutely right. And here it is, peering DB. Just see what this one has to say for itself. Fine. So you can look for an AS5086 or whatever you like. Fine. And we could just look into whatever we want to look into. So there is an awful lot of information available. The organization, IT Telnet, AS number, fine. I'm just picking these up at random, yeah. But just be aware you are not an island, yeah, or the system is not an island. They are part and parcel of a greater being, yeah. Protocol supporter, unicast, multicast, maybe. The architecture, the IXP architecture. By the end of the chapter, you will be able to describe the architecture of the IXs. Yeah, potentially. There it is. The internet without internet exchange points. It's a fully meshed network. Now, I said before, if we have 6 nodes, which we do have here, the formula is 6 multiplied by, in this case, 6 minus 1. Actually, start again there. The formula is the number of nodes multiplied by the number of nodes minus 1 divided by 2. So 6 multiplied by 5 is 30, divided by 2 is 15. There will be 15 connections in there. Yeah, not going to count them just in case I've missed them. But this would be without internet exchange points. How many connections would be needed for a fully meshed network if there was 8 nodes to be connected? Well, that would be 8 multiplied by 7 is 56, divided by 2 is 28. So you can see, when I said on the 6th one, 6 multiplied by 5, 30, divided by 2 is 15. Just 2 more nodes gives an increase of 13 connections. So, you can get some connections for sure. So the IXs play a fundamental part, a very big part. There it is. So now, what can I say? So this device here is now supporting all of these. Now, okay, I know you would need more than one connection, yeah? Or you probably would want more than one connection, but it proves the point. The IX gives you far fewer connections, okay? IX and routers on here. We've now got our customer edge devices here. Absolutely right. We've got our provider edge devices here. Absolutely. And again, these are all interfaced into this layer 2 system. So fine, it gives you that point of contact. Absolutely. And there's the peering taking place. Yeah. So this device here is peering up here, peering over here. Fantastic. And this device is peering over here. All well and good. So everything is looking pretty real. Okay. The costs. What costs are you looking at? Yeah. There are 3 main cost areas to consider when you are joining an IX. Yeah. The access, not the least, the access itself. There is rack space. Yeah, you've got numerous devices, good heavens, and then you've got the fees themselves, for data delivery, for monitoring. So, yeah, absolutely right. There are root servers. Again, root servers, instead of peering with everyone, the service provider needs only peer with the root server. So you peer with the root server, and life is good. Yeah, as do these, rather than peering with everyone. It makes perfect sense. Yeah. Regionalised, absolutely right. There are multiple locations. LINX are in Scotland, Manchester, London. So, good old coverage, really. The looking glasses themselves, we've already seen. We can go into here. BGP, border gateway, BGP. See what it has to say about itself. There is another one, BGP, the Border Gateway Protocol Advanced Services, Looking Glass Service, BGP tools, utilities and software, lots of other reference materials as well. So there is no shortage of materials at all. So what do you want to do? You go into your Looking Glass, you can generate your queries, you can have a look for summarizations, have a look for the whole thing. which brings you to best practice, right? Look at this. Oh, aggregation. Surely not. Yeah. By the end of the chapter, you'll be able to recognize the value of prefix lists, AS path filter lists, aggregation. What on earth are all them? Goodness me. Well, the fact of the matter is that we do have help on this as well. Yeah. Here's another website. We can see here the aim peering best practice. The idea is there to prevent the receipt of prefixes that you shouldn't get. Whoops, there's he, sorry. Hello. Yeah, prevents anybody transmitting and or receiving prefixes that they shouldn't, that they don't want to, they don't want to receive. You could use prefix lists. You can use AS path filter lists. Absolutely right. Yeah, fine. You can aggregate, as we've already seen. The aggregation itself takes up less memory space. It's a fact. Yeah, and you see now reasonably straightforward that was to do it. Yeah. So here, the aim is to prevent the receipt of prefixes that can interfere with our network. Yeah, or could cause traffic to be wrongly routed. Absolutely. General filter. You should only accept prefixes that are in the agreement. You should accept only prefixes with those with a certain AS number. Now, this is a big old deal because if you remember, when I was doing that first lab, I said, look, in the AS path attribute, there are a list of AS numbers. The rightmost one is the origin. So suddenly you can filter using AS path filter lists, and you can only accept information that has originated in AS 2010. You could actually accept information that has transited through AS 2010. You could actually filter so you only receive information that the last step, the last hop to you was AS 2010. There is a lot of filtering capabilities. Prefix lists themselves are super powerful. Yeah, they can be configured to filter on whatever you like. Yeah, they can do full networks, they can do subnets, they can do all sorts. They can also incorporate the subnet mask length. So you could say, I only want to receive networks 200.10.10. I'll tell you what, we'll do networks 200.10.10.64. Yeah, so that would give us a bit of a prefix list. And then you would say with subnet mask greater than or equal to 26. Yeah, where 26 is your /26, 255, whatever it is. Yeah, so you can be very selective. Okay.
Richard, can I just stop you there? We have our first question.
Good heavens. Yeah.
So remember, guys, get your questions in the Q&A function.
Is the question, is he ever going to stop talking?
No, not yet. But Rebecca asks, what is the peering best practice when it comes to having two different transit providers?
Two different transit providers. All right. Right, that's a good question. So, and what is the best practice? Well, presumably, would one be a primary provider, and the other one be a secondary? So in that case, you would, yeah, what you would do there, you would use the attributes to send it out on a certain link to the primary provider, and then you would also ensure that you only receive it on that same link. Does that make sense?
I think so. They'll let us know if it doesn't.
No, it doesn't. Yeah. So what I'm trying to say is, if you have two transit providers into your system, I would have thought there's probably a primary and a secondary. One would be the primary, one would be the secondary. So you could then, on a per customer basis, you could send information out to your primary, and then that would then encourage the response to come back in on the primary connection. Or you could then, again, on a customer type basis, you would then send it out to your secondary provider, and the response would come back in. So it wouldn't be asynchronous at all. It would still be synchronous.
Perfect. Thank you. Yes.
Does that help?
Yes, primary and secondary. So that answers it. Thanks, Richard.
Great stuff. And at least you know how to pronounce asynchronous now then, Holly.
Yes, all right. I know what it means. Thank you.
Yes, just think when you're out to the Pizza Hut tonight, you could ask for a piece of asynchronous pizza. Yeah, excellent. Great stuff. So there you go. Within here, so this filtering, yeah, you are accepting certain information for sure. You can set limits. This is to try and prevent overwhelming the processor, basically. Yeah, get rid of prefixes that you don't want. Absolutely right, and so on and so forth. You can filter left, right, and center. Okay. Prefix filtering here. There are two ways. There is a prefix list. It is easy to use. Prefix lists, I've used these for years, and a lot of people don't realize just how powerful they are. Yeah, but the fact of the matter is, you can it's terribly scaled, terribly granular. You can filter out complete subnets, absolutely right. Complete subnets in cooperation with the subnet masks as well. Yeah, the AS path filtering, this is great. Yeah, you can interrogate the AS path attribute. You can say, quite literally, I only want information that has been originated from AS 2010. That's it. That's it. Boom, finish. And that's what you would get. You can include this in your in the reporting mechanisms as well as regular expressions, you know. So you can also say, I only want a list of information that has come in from the next hop to me when it's 2010. Yeah. Or you can say, I want to filter the AS path attribute list and I'm looking to set for anything that has transited across AS 2010. Absolutely brilliant. Yeah, absolutely brilliant. Yeah. Within them, you can use route maps. You can then incorporate your prefix list in there with the permits and with the denies as well. So that it is terribly granular, as I say. And there we go. Now look here, these prefix lists here, if we just pick on, I don't know, we'll say this one here. No, I'll pick on an IP actually, all of these are all prefix lists. This is the name of the prefix list, IP prefix list, RFC 1918. That's what you decided to call it. You are then denying everything here with there that is less than 32. This here, less than or equal to, this is a subnet mask. Yeah. So you are going to deny all hosts in this case. Yeah. Here, less than 8. There, that business here is just looking at the first 8 bits here. All right. This is quite important. This here, if I jump down onto this one, this /24 here is indicating these 8 bits here, these 8 bits here, and these 8 bits here. This is nothing to do with the subnet mask, right? It is saying there are 24, but I want to make a match on these 24 bits, where the 24 bits is them 8, and them 8. So basically, this is going to deny 192.0.2 everything. This here is the subnet mask, yeah? And so is this, and so is this. This and here. How about this then? Permit everything, yeah, that has a 0 here, less than or equal to 3. Yeah. So this is an awful lot of information through. But so prefix list, they need a little bit of work just to get used to them. Yeah. Again, at the risk of being a bore, 172.16 IP prefix list RFC 1918 deny 172.16.00/12. That 12 here is incorporated these 8 bits, these 8 bits here, and the first 4 here. So that will be the 128, the 64, the 32 bit. Yeah. So basically, it's going to be looking for 172.16s. That's it. Yeah. And then it's looking again at the subnet mask for less than or equal to 32. So these are really powerful stuff. And what we've got in here, this is how you apply it. Yeah. Under the BGP process, you've got a neighbor 192.32.231.200, remote AS 65200. Well, we can see here our BGP process is 65564. This is 65200. This is not 65200 is not 65564. 65564 is not 65200. Consequently, this is external BGP. Then, having declared our neighbour, we then say, look, I want to apply to this neighbour prefix list RFC 1918, data coming in, and prefix list data coming out. Fine. Another one, remote AS 652.110, still not that one. So it's external BGP. And there you are applying a prefix list again. Brilliant. That's how you build them. That's how you apply them. Using AS path filters. Tremendous. Now look here. Filter routes based on the AS path, just like as I said. It is applied the same way as a prefix list. It is, because we have a neighbour here, then we apply our filter lists. And all right, AS path syntax can be different, but what we're looking at here, dead interesting. We are building, where is it? We've got filter list number 1, fair enough, out of the filter list, all this business. Here's my AS IP AS path access list number 1. Permit. Look, this is now saying it's got these two fancy little symbols here. This is saying I want to permit only information. No, I'll rephrase that. I want to permit information that only has 65564 in its AS path. Yeah, because this is the start and this is the end of the path. So here you are isolating 65564. So that would permit information that has only got that in its AS path. And similarly here, IP AS path 200, there's your 200, yeah, filter list 200 here, permit information that only has 65200, yeah, in the AS path. If you just, I put my cursor over that caret symbol, that one now was saying permit anything that, yeah, there, I put that there, that's a stupid thing. Right, that is now hopefully obscured the caret. So that would now permit anything that has originated from 65200. Or that one, that would permit anything that at the last hop from 65200. But when you use the two together, it means only. So it's the start and the end, and they've only got one entry in between. Fine. There it is. There's the beginning of the line, the end of the line. That's as you read it. And you can see here, look, yeah, look, that means nothing. I am only interested in information that is local to this AS. Fine. That is information originated by 3856. There's the end of the line. There's 3856, separated by a space. Oops. Hello, hello. What's happened here? I must have caught something. Sorry. Do this. Best practice. Right. Finally got back to it. Yeah. So here, local to this AS, there's nothing there. Here, originated by AS, originated by AS3856. There it is, the end of the line here, and just a separator that is only looking for 3856. That separator there prevents you finding 13856, 23856, 73856, that kind of thing. And then information received from, again, received from at the end, 3856 underscore, that would prevent you getting from 38560, 38561, etc. Yeah, transited, information has transited through 3856. Absolutely. This is a bit risky, really, because here we're saying it's gone via 3856 and AS42. Well, it has if they're in that particular pattern, but otherwise you'd have to find a better way of doing that. I'm not a big fan of that one, but you never know. So there you go. That's the summary. So that's very important stuff, this here, this prefix filtering, the AS path filtering, and of course the aggregation. So essentially that, when we get to here, you will be able to go home. And that's exactly it. That is the last slide, so you can all go home. There you go. Thank you very much. I hope you've enjoyed that. Over to you then, Holly.
Perfect. Thank you, Richard. That's perfect timing. Just before we go, we've got one last question. So Aura asks, how are emerging technologies like SDN and automation, like peering DB, APIs, IX APIs, being integrated into IXP operations?
Good heavens. Well, SDN, there is some talk about it now, actually. So SDN is in a work in progress, basically. In fact, automation's been around for a long time. Yeah, so that is definitely in there. That's all I could really say. Yeah, so it's all works in progress. Does that help?
Perfect. Thank you, Richard, and thank you again all for joining us. We hope you enjoyed this session. Now, remember, if you have any other webinar topic suggestions, get in contact with us and we can look into this for you. So we have loads of other webinars coming up, so make sure you get yourself registered on those and keep an eye on our events page to find out where we are in the world and what free sessions we have coming up to register for. So thank you very much for attending, and we hope to see you again soon. Goodbye.
Thanks, Holly. Thank you, everyone.